I now call to order the Society's 2,447th meeting in the 150th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's lecture by Fengchuan Liu. The Society has been meeting and hosting lectures via Zoom for over a year, starting with the Joseph Henry Lecture on May 15th, 2020, almost a year and a half ago now. Meetings this fall, thus far, have been done via Zoom as well, due to COVID-related restrictions here in DC, and also restrictions on speaker travel. We remain optimistic, nonetheless, that the Society will be able to meet again in person by the end of the year. Of course, we are at the mercy of the pandemic and the measures the authorities institute to deal with it. While we hope for the best, whether in person or not, the Society will continue meeting and live streaming events, and it will continue working on how to best utilize the new tools of video production and social media to bring science to everyone and enhance the value of PSW membership. The Society is grateful to the sponsors of the 2021-2022 lecture series for their support, the Policy Studies Organization in cooperation with the American Public University, and a generous donor who has asked to remain anonymous. Please join me in thanking them. Thank you, sponsors. And tonight, we'd like to offer a special thanks to PSW member Joe Schulman for sponsoring two meetings, number 2,446 on October 8th, 2020, on adaptive optics, given by Olivier Goyon, and number 2,436, given on March 5th, 2021, on building the Giant Magellan Telescope by James Fanson. Thank you, Joe, for sponsoring those two lectures. I'm pleased to announce that the following new members have been elected to the Society. William Schultz, Managing Editor of Photonics Focus, published by the International Society for Optics and Photonics, interested in a wide variety of the sciences, especially quantum electrodynamics, photonics, quantum computing, and astrophysics, who learned a PSW from Ivan Amato. And tonight's speaker, Fengchuan Liu, whose interests will be clear to you a little part from tonight's proceedings. Please join me in welcoming them to membership. Welcome. Recording Secretary James Heelan will now read the minutes of the 2,446th meeting and the lecture by Olivier Goyon on adaptive optics, taking the twinkle out of the stars. James, the screen is yours.
Thank you, Larry. Good evening, everyone. On October 8th, 2021, by Zoom webinar broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2,446th meeting of the Society to order at 8:02 p.m. Eastern Daylight Time. He welcomed new members, and the recording secretary read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, Olivier Goyon, professor of astronomy and astronomer at the Stewart Observatory at the University of Arizona. His lecture was titled, Taking the Twinkle Out of the Stars, How Adaptive Optics on Ground-Based Telescopes Delivers the Sharpest Images of Our Universe. The Subaru Telescope is an 8-meter telescope atop Mauna Kea in Hawaii, where Goyon leads the Coronagraphic Extreme Adaptive Optics group. Building telescopes with larger primary mirrors that collect more light are necessary to increase image resolution and see deeper into space. Goyon explained diffraction by circular aperture, which produces a bright center surrounded by diffraction rings. In principle, this airy pattern is inverse linear related to the diameter of the telescope. The bigger the telescope, the smaller the pattern. But in reality, atmospheric turbulence limits the angular resolution of traditional ground-based telescopes. For this reason, the 2.4-meter Hubble Space Telescope achieves significantly greater resolution than much larger ground-based telescopes. In the 1990s, scientists began developing adaptive optics for ground-based telescopes. In principle, adaptive optics corrects aberrated light using a mirror that can quickly change shape to exactly compensate for the optical distortion. The system uses a wavefront sensor to measure the shape of the distortion in real time. In the 1990s and early 2000s, adaptive optics were only effective on relatively bright objects. Fainter objects produced insufficient light for older adaptive optics technology to quickly enough correct the atmospheric turbulence. Recently, laser guide star technology that creates an artificial bright spot in the sky has revolutionized adaptive optics technology. Guillaume used still images and animations to demonstrate the effectiveness of this technology in galactic center observations. We note, in our 2436th meeting, Speaker James Fanson informed the Society about the laser guide star technology being installed on the Giant Magellan Telescope currently under construction in Chile. Guillaume said the next big revolution in adaptive optics is to expand the field of view. Doing so requires multiple correcting mirrors and multiple, either natural or laser, guide stars. This technology already exists in the Gemini Multi-Conjugate Adaptive Optics System, or GEMS, which uses 5 laser guide stars to produce high-resolution wide-field images. The speaker's specialty is in high-contrast, extreme adaptive optics. He's designing systems aimed at finding and imaging exoplanets, which does not require wide field of view. The technology is extreme because it exquisitely corrects wavefronts aberrated more than a micron to produce an image limited by diffraction. Guillaume and his team then deploy a coronagraph to remove the diffraction, allowing them to then search the image for planets closely orbiting the subject star. Imaging planets allows spectroscopy to measure atmospheric composition, which may reveal evidence of life on a planet's surface. The speaker used a spectrum of Earth, obtained by observing Earth's reflection on the moon, to identify the kinds of biomarkers that scientists hope to find on exoplanets. It has been hard to image habitable exoplanets because the planets are millions to billions less bright than the stars they closely orbit. The speaker then described the Subaru Coronagraphic Extreme Adaptive Optics System. Because the telescope's field of view is so small, it is able to condense light from the 8-meter primary mirror to a beam only 2 centimeters wide. The telescope then uses extreme adaptive optics to correct atmospheric turbulence, a coronagraph to mask the light of the bright star, and smart image processing to recognize planets. Guillaume used images to demonstrate each step in the system's process. He said his work is validating technologies for use on larger telescopes, like the 30-meter telescope, the Giant Magellan Telescope, and the European Extremely Large Telescope. These telescopes will transition scientists from imaging only Jupiter-like planets to imaging Earth-like planets around nearby stars. The speaker described the GMAG AO-X that will be installed on the Giant Magellan Telescope to observe the southern hemisphere. He then described the TMT Planetary Systems Imager that will observe the northern hemisphere. The speaker then concluded and answered questions from the online viewing audience. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. President Milstein adjourned the meeting at 9:41 p.m. The temperature in Washington, D.C., 21 degrees Celsius. The weather, mostly cloudy. And the number of concurrent viewers of the Zoom and YouTube live streams, 70, and views on the PSW Science YouTube channel and Vimeo channels, 246. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. The minutes will be posted to the website in due course. Please send any corrections or comments on the minutes to corresponding secretary, Robin Taylor, at correspondingsec@pswscience.org. We now turn to tonight's lecture, 12 times Hubble and halfway to space, the 30-meter telescope. It is my pleasure to introduce tonight's speaker, Fengchuan Liu, Fengchuan is the project manager for the 30-meter telescope project. He's had a long and distinguished career in the management and engineering of large space missions and science projects, including serving as project manager of NASA's WISE, NEO-WISE, and NEOCOM missions, and as deputy project manager of the NISAR and LTMPF missions. He is an author on numerous peer-reviewed journal articles and conference proceedings, and he is the recipient of a NASA Outstanding Leadership Medal, a NASA Exceptional Achievement Medal, and the JPL Magellan Award. Fengchuan earned his BS in physics at Nankai University and his PhD in physics at the University of Washington. All questions will be fielded after the lecture during the Q&A session. Fengchuan, the screen is yours.
Thank you very much, Larry, for the kind introduction. It's a great honor to be here. First, I want to acknowledge a number of my colleagues here from the project. They're the ones who really make the project click, designing and building this. And if there are questions I cannot answer, they will also be helping me answer those questions. So over the last 400 years, the telescope size for optical telescope has really increased from the original few centimeter size that Galileo used to observe the planets to today's 10-meter class telescope as represented by the Keck observatories. For each major upstep in the telescope size, we learned much more about the discoveries. And first, we learned the solar system, then our own galaxy, and then the universe beyond. And we believe that as we design and build the next generation 30-meter class telescope, it'll bring discoveries of new physics and new worlds. So the 5-meter Hubble telescope was constructed over a course of over 20 years. It was slowed down by World War II, but people realized that we're getting close to the upper limit of a single side a monolithic mirror. It was getting difficult to cast, polish, and to actually transfer out the summit. And subsequently, you've heard a lot of 8-meter class mirrors being built, including the ones that go into the Giant Magellan Telescope. It was the late, great Professor Jared Nelson who realized that to build anything 10-meter or bigger, you really have to resort to the segmented mirror telescope. And he became the father of segmented mirror telescopes. This is a paper in 1979 by Mast and Nelson. They demonstrate that with a hexagonal shape segmented mirror, and if you can place simple capacitance display sensors across the edge between the two segments and coupled with actuators behind each segment and computer controls, you can really phase these segments in optical wavelengths, and so that they behave like a monolithic mirror. And this is the sketch of the primary mirror design and the telescope design. And subsequently, they collaborated with Keck Foundation and Caltech, and the rest of its history. The size matters first because it collects more photon, and then because there's this thing called diffraction limit. And if you use a telescope of primary mirror size after D to image a point source far away on the image plane rather than a point, you get a theoretical limit disk. It's called an area disk. And the angular size of this disk is inversely proportional to the diameter of the primary mirror. So this means as the telescope size increases, you have a sharper image and you have a better resolution of point sources nearby, far away. But more importantly, if you're interested in the sensitivity of faint point source far away, you're looking at collecting d squares more photon over a 1 over d square area. So you really gain the sensitivity by d to the 4th power. And this is really where size matters. So in comparison, for 30-meter telescope compared to 10-meter Keck, the theoretical diffraction limit resolution is about 8 milliarcsecond. And this is quite remarkable. It's about looking at resolving a quarter from 500 miles away. And compared to Hubble, this is 12 times better. And actually, for reference, the central obscuration from TMT primary mirror is about 3 meters. So it's actually bigger than the Hubble primary mirror. But this is really not a fair comparison because Hubble being a space telescope, it's free of atmospheric disturbance. On ground, the atmospheric disturbance limit your angular resolution to no better than half an arcsecond. This is called the seeing limit. And you've heard this in the last lecture. And that is assuming that you put your observatory on the really good mountaintop there. In this science paper in 1981, the author stated Mauna Kea being halfway to space is the finest astronomical site in the world. The atmosphere above the summit is stable and dry and clear, and there's very little light pollution. And the exceptionally dry air about Mauna Kea is especially important if you want to study exoplanets or planets, which tend to radiate more infrared light, and because you have less water vapor to absorb the infrared light. To overcome the seeing limit, the adaptive optics was developed 30, 40 years ago. You heard a lot from the last lecture. So the basic idea is if you can detect the atmospheric disturbance and you can characterize it and command a deformable mirror on the optical path to correct for this disturbance, and you have to do that in near real time, then you can have dramatically improved image. And this technology is used on all the large telescopes now, common to all of them, and it really makes the ground telescope much more capable and much more competitive, at least for these near infrared wavelengths. I'll come back to this later. So with the AO technology and the mirror facing technology, we're ready to build the next generation 30-meter class telescope. We know that Europe is building a 39-meter extreme large telescope in southern hemisphere, Chile, and it's under construction. It's also using Keck type of technology. Nearby, a US-led international consortium is building the Giant Magellan Telescope, and that lecture was given back in March. And this put together 7 round mirrors and to form a equivalent 25-meter telescope. The only 30-meter class telescope in Northern Hemisphere is TMT. And so the idea of a US extremely large telescope was formed a couple of years ago, and is to combine TMT and GMT to seek National Science Foundation investment for at least 25% of observing time in each of TMT and GMT, plus the NSF's optical IR lab. And this program is currently being reviewed by national academies through the Astro 2020 decadal survey process, and we believe the report should come out in the next couple of weeks, and we anxiously looking forward to positive report. The case for both telescope is very strong. And first you have all sky axis, and it here shows the northern hemisphere covered by TMT and southern hemisphere covered by GMT, and in the middle accessible to both these ELTs. And it gives a good chance to look for rare targets, and gives you more hours on the sky, and actually different hours on the sky between these two telescopes because of longitude difference. And this is very good for time domain multi-messenger astrophysics. It also gives us more opportunity to try out broader instrument suites. So the TMT detailed science case was documented in the science books, has been since 2015. You can access that tmt.org, easily find it. And TMT will address all the big questions in the astronomy. What is the nature and composition of the universe? When did the first galaxies form? How did they evolve? What is the relationship between black holes and galaxies? How do stars and planets form? What is the nature of exoplanets? Is there life elsewhere in the universe? And the theme of the science book is characterized by solar system, exoplanets, stars, supermassive black holes, galaxies, early universe, fundamental physics and cosmology, as well as time domain science. Since I'm not an astronomer, I will show you some examples what TMT promises to do. And first, in our solar system observation of Jupiter's moon Io, which has volcanic activities. On the left is what Keck can do with AO, and in the middle is what TMT can do with IRIS near infrared. And with this kind of resolution, you can observe volcano if it has one. On the right, you have a much better, sharper image by Galileo, but it was taken by cameras in close proximity. Another Jupiter moon, Europa, and it's believed there's an ocean under the frozen surface, and perhaps there's some kind of life under there. There's a lot of interest in this. In fact, Hubble Telescope has detected plumes on the surface. And just last week, I read that in the trailing hemisphere, there's water in the atmosphere. So there's a lot of interest in this. Further out in the solar system, Kuiper Belt, you can study Pluto and its moon Chiron. And for reference here, the angular resolution of TMT of 8 milliarc second is a factor of 6 or 7 smaller than the Chiron, the diameter. And so this is a direct imaging of exoplanet system about 130 light years away with coronagraph blocking the starlight. You can see 4 giant exoplanets here. Display is not doing very well. But anyway, with this kind of imaging, you can collect the exoplanets light and do a spectrum to see if there's biomarkers there. What TMT contribute to this is these are giant Jupiter-sized exoplanet. What TMT can do is to be able to detect smaller exoplanet, perhaps closer to the host star or fainter, or exoplanet system further away, or combination of all these. Professor Andrea Guess of UCLA, who is also a member of the TMT science team, won Nobel Prize last year for her work studying the galactic centers, where there is a supermassive black hole of 4 million solar mass. Using Keck with adaptive optics, you get a much sharper image. And the study of stellar motion is traced back to 1995. And this is a very strong gravitational field. It's also a place to test Einstein's theory of general relativity. So what TMT can do is dramatically improving the study of galactic center with better angular resolution and better sensitivity. So in nearby galaxies, here is Andromeda, and compared to Hubble, TMT would be able to, with AO, resolve individual stars and look at the star populations. Another field we can help, TMT can help, is the studying dark matter through gravitational lensing. And here illustrates as light from a quasar far away is bended by a dark matter field and amplified and form multiple images and in this structure. And TMT will be able to have refined study of these and deduce back what the dark matter field looks like and distribution. And with dramatically improved sensitivity, we can push the boundary and look at the first galaxies and for detecting first galaxies and first stars. So in summary, from today's solar system to when the first galaxy and first stars formed and everything in between, TMT should be able to contribute to studies all over this field. So now I'm going to change gear to look at the TMT system architecture. The telescope design is Ritchie-Chrétien, traditional telescope design shared with Keck and Hubble. This gives you a field of view of 20 arc-minute or unvignetted 15 arc-minute, and it does a good job of correcting for aberrations and coma. The primary mirror is 30 meter in size, hyperboloid. Secondary mirror is a convex, 3.1 meter. And tertiary mirror is a flat mirror, 2.5 by 3.6 meter. And there's no power. It can rotate in 2 axes. Its only purpose is to direct light 2 science instruments that sits on the both sides of Naismith's platform. You can see they are represented by boxy structures. So TMT is funded by a global public-private partnership. Private funds come from Caltech and University of California system. They are all cash partners, and thanks to the generous contribution from the Gordon Betty Moore Foundation. And the public funds, both in kinds and cash, come from the government of Japan, India, and Canada. China has a consortium led by the National Observatory and Chinese Academy of Sciences, various institutes and universities, and they also contribute in kind and cash. And as I mentioned, we're anxiously waiting for the decadal results and looking forward to the participation of National Science Foundation as an all-cash partner through the US EELT program. So this is just a fly-through of the observatory, and this is a colloid type of dome. You can see the flaps deployed and the shutter opens, and we're looking down to the primary mirror and the back of the secondary mirror. And the tertiary mirror in this simulation is floating. And you can see on the walls of the dome, you can see the vent windows. There are a total of 88 of them. And now you're zooming out. In comparison, you see figures, humans in those windows, fully deployed flaps. And behind the secondary mirror, there's a laser light coming out for adaptive optics, laser guide stars. So the whole system design is actually quite mature. We counted roughly 82% of the subsystem either in final design or beyond final design. We're done with design in various stages of fabrication. And the dome itself is an in-kind contribution from Canada, and the design is completed. You see this, the flaps here open, deployed, and when the shutter is closed, it just seals the shutter. When the shutter opens, it guides the airflow to minimize the vortices and improve the seedings above the telescope. And these type of designs are guided by a lot of aerothermal simulations using computational fluid dynamics. Here is just a simulation. This type of study really help us to understand the environmental impact on the image quality and improve the image quality and minimize impacts such as wind and heat dissipation. And another feature of the colloid dome design really is to minimize the overall profile, the size. And we try very hard on this. And for comparison to Subaru and Gemini telescope, TMT primary mirror is 3.5 times the size, and yet the dome is only 20–30% taller. And it's actually 10% lower than the Giant Magellan Telescope, even though our primary mirror is about 20% bigger. And here shows just halfway through the construction of the dome. And you see false works, a lot of it to help the construction. And I want to show this because for every one of these major configurations, we analyze it for the seismic strengths and to make sure it survives the seismic event. And this shows when the observatory is nearly built out, and the rest of the summit facility is responsibility of US contribution. And the site, as you can see, is about 500 feet below the summit. Now I switch gear to look at the telescope structure. And this is the responsibility of Japan's Mitsubishi Electric Corporation. And what you see here is over 3,000 metric tons of structure, both the fixed structure and the moving structure, plus the attachment, the science instrument, telescope, all of these. Mitsubishi has a lot of experience building Subaru telescope, and this design is quite complex. It has many challenging and competing requirements, such as seismic requirement you have to meet, have to generate very little vibration for AO type of instrument. Vibration is quite a sensitive issue, and it has to minimize thermal dissipation, and it has to be agile. And the requirement is that you can point from any target to any target in no more than 3 minutes. And in a typical observation sequence, the estimate is about 1 minute between target and target. This really maximize the time you spend on science. And the pointing has to be accurate and steady. Here just shows on the left the azimuth structure, on the right the elevation structure, a little more details. Telescope utility service includes things like power, air, thermal, water, refrigerant, liquid nitrogen. These are not high-tech items, but it requires tedious, meticulous system engineering and interface definition, particularly when we have multiple developers all over the world. Here's just one example in the lower one that shows the pipes and cable trays run up the azimuth structure and all the way to the elevation structure. On the right, it shows the liquid nitrogen system, all the pipes involved from the pinto bearing at the bottom to the side of the azimuth structure where the science instruments are located. So I want to change gear a little bit to look at what makes TMT a powerful science machine. There are many things, but there's three things that stand out: the 30-meter primary mirror, sophisticated AO system, and powerful science instruments. So we'll spend a bit more time on this. So the primary mirror here, for comparison, is the person standing next to the left. And it has 492 segments plus 82 spares. Each segment is 1.44 meter across corners and 45 millimeter thick glass. It's not lightweighted. And the total area is 652 square meters. And when I emphasize the gap between segments is only 2.5 millimeter, we really try hard to minimize this gap. This leaves about 0.6% of the loss area. What this does with a field aperture is to give you a well-structured point spread function on the image plane. With so basically, there's more light focused into that central area spot and gives you a sharper image. And there are 6 identical sectors for these 492 segments. Each sector has 82 segments, and these 82 segments are all different, as different as spherical prescriptions. And even the shape is not exactly hexagon, slightly off. This image shows there are 4 countries involved in producing these segments. In the middle, Japan produces 30%. And next to that is US producing 40%. And both countries are in actual production right now. India and China round out the rings 15% each. And for each party, you also produce the spares as well. And Japan's Ohara Corporation provides all the mirror blanks. And this is clear SRAM. This type of clear SRAM really gives you zero thermal extension at 0 degrees Celsius and very small expansion in nearby temperature. This is where we care about. And here just shows the glass is poured into the mold at up to 1700 degrees C. And the workers are preparing for a 3 months annealing cycle. And after that, you can slice these build to give us 7 or 8 mirror blanks. And I counted they have 12 annealing ovens. So my math tells me they can do, if they go full speed, they can do 300-400 of these mirror blanks for us. And that's about how much we have for production a year. We have so far 362 blanks produced, and that's about 60% of what we need. And that includes spares. We have some of these stored in US as part of the production efforts, and some in India now as they get ready to produce. So next is polishing. And this is a setup at a US company called Coherent in Bay Area. There is a company under a different name that polish for Keck mirrors. And these set up polish mirrors to spherical shape. But our mirrors are aspherical. And so the solution to that is called stress mirror polishing. Again, this was used on Keck first. And the principle is quite simple. You support the mirror blanks and you glue a set of 24 pairs of actuators around the edge. And you can apply stress to these actuators that bend the mirror create a deviation from spherical opposite to what you want eventually. Then you polish it to spherical shape. You take off the stress, and the mirror will spring back and relax to a shape of spherical shape that you desire. And you can repeat that process if you want. So this is give us a way to polish into spherical shape under stress, eventually producing aspherical. And Japan led this effort. I don't have image to show here, but they have polished over 30 of these roundels. And in US, and here shows the operation that Coherent, they have delivered 13, and they are ramping up the production to about 3 or 4 per month. And this, at the end of polishing, gives you less than 2 micron peak to valley surface area. And on the lower right corner is a metrology setup we call 2D profilometer. What it does is it has a set of 60 probes, mechanical probes. And each one is called LVDT, or linear variable differential transformer. And so it basically turns a position signal into electric signal through a transformer. And so what this does is, as you lower the set of probes to the mirror surface, it gives you a 2-dimensional profile, and you can rotate and gives you better sampling. And this is the setup that we use in all partners to give you metrology that can tell you whether you're done with polishing. And China used the same stress mirror polishing technique, but they built a much bigger machine. This machine is over 5 meters in diameter, and it can polish 3 roundels concurrently. And the machine actually works, and they're trying to figure out some fine tunings and getting ready to polish next year. They've demonstrated they can meet our requirement. In fact, this is a similar setup they used to build the Lamotte telescope in China. After polishing, each partner will do hex cutting. It's machining out the shape into a near hexagon shape, and also machine out the pockets at the edge for edge sensors, and also at the back center of the roundel, you have a pocket there. We'll come back to this. So Japan and US have both demonstrated can do this, and China and India have bought the machines. They're getting ready to try this out. So now after the machining, you mount it on a segment support assembly, SSA. SSA provides passive support as well as active control of the mirror figure. The passive support comes in axial direction with a 27-point whiffletree structure to spread out the load. And you can see here the rod flexures glued to the back of the mirror. And the lateral constraint is provided by this central diaphragm in the lower figure that's glued into the pocket we just saw machined out of the back in the center. The active control has 2 components. First, the tip tilt piston is provided by 3 large actuators, and these are represented by the pink on the side. And then you have 21 warping harness actuators that's built into the whiffletree structure. So what they do is they apply stress to bend the mirrors at nanometer level to improve the surface figure. And this is quite important to correct for things like thermal gradient or gravity gradient. So it's a quite complex support structure here. So now you put together, this is an image that shows the central diaphragm, the smaller circle in the middle, and all the whiffletree structures and bells and whistles in the back. So now we're ready to improve the surface figure from about under 1 micron RMS to under 10 nanometer RMS. That's an improvement of factor of 100. We do this by ion beam figuring. And so accelerated argon ions would bombard the surface and move materials 1 layer at a time. And as the Keck, this is an image from Keck. To do this, you need a very fine, high precision metrology system. And this is an interference-based metrology system. Our mirror segments at the bottom is aspherical, and the test plate, you only have 1 spherical shaped reference test plate. In order to be able to do interference between these very different shapes, we use a computer-generated hologram, CGH. It's a diffraction pattern. What it does is to change the wavefront, modify it such that when that wavefront is reflected from the DMT segments, aspherical segment, it's very close to a spherical shape. And then you have another beam that's not modified by CGH wavefront, and that's reflected from a spherical test plate. And these two waves can do interference and gives you a high precision, high resolution metrology. And this system is very neat and was designed and built by Arizona Optical System, and it's already delivered. It's in our storage. Eventually, this will be installed in the IBF, I-beam figuring vendor facility. And here on the right is just a schematic that shows at the top you have the beam launching interrogating imaging system. At the bottom, you have the TMT segments, aspherical segment that's seated a few millimeters below the spherical reference test plate. Now, when you add all the sensors, actuators, and you form a complete primary segment assembly PSA, shown here, the total mass per segment is about 274 kilogram each. And among all the segments, 492 segments, you have nearly 1,500 segment actuators, 2,700 plus edge sensors, over 10,000 warping harnesses to change the figure of the overall M1 mirror. And you have a lot of electronics supporting all this, but these are all relatively low power and there's no active cooling required. And we have one unit a few years ago, one segment that was vibration tested to make sure that it survives the seismic events. And the key here is every 2 years, we need to recoat the surface to improve the reflectivity. And so the approach we do is instead of coating them all together, we coat 10 of them every 2 weeks. So over the course of 2 years, they get all rotated and entire mirror is recoated. And we do that during daytime over a course of 10 hours. And the only way we can do that with 10 hours and test segments is to use robots. And here shows a segment handling system that's designed by Mitsubishi Corporation in Japan. This is just animation. It shows that segment handling bridge comes down, latches to the side of tertiary mirror, and rotates around, and another connecting bridge comes down. Now you see this robot sliding through, and it has a high quality vision system. It knows exactly where the segments is that needs to be replaced. A worker below the mirror will push up the segment, and the arms will come down and pick it up. And it has the force sensors to make sure it does not damage any mirror segments. And it moves to the edge, and then you put it on the handling fixture. And the system is lower to the floor, probably slower than that. And then you pick up another segment that's freshly coated. So the spares are more than spares. They are part of the rotation in this coating operation. So every 2 years. So in our laboratory in California, we built a multi-segment integration test facility. This can host up to 7 segments shown here. These are aluminum dummy mirrors, but nonetheless, the purpose here is to try out all the installation, assembly process, and procedures and toolings included. And it's been very helpful in guiding our design and integration process, risk reduction as well. From below, you can see the 2.5 millimeter gap between mirror segments. You can barely see that. And in these, what we call dust boots, that enclose the capacitive sensors and keep the dust out. And you can also see this rod flexures from the part of the riffle tree that's glued to the back of the mirror. Now I will change gear here to look at the first light adaptive optics instruments and science instruments. And these are all installed on the Naismith platform on both sides of the telescope and in reference to the telescope mirrors. So I will just mention a little bit of the AO. the basics. If you have a reference star and starlight goes through the atmospheric turbulence, and if you collect the light and send it to wavefront sensing and characterize the disturbance, and the real-time controller will command a deformable mirror to change its shape and counter the disturbance that you characterized. And if you can do this fast enough, nearly 1,000 times per second, then you can have a corrected image of sent to the science cameras. But since there is not always reference star available for the field you want to study, you can use lasers, and these are lasers of 589 nanometer wavelengths, and the laser can excite sodium atoms in the mesosphere about 90 kilometers above us, and this will generate artificial guide stars, and it's called laser guide stars. And you can generate multiple of these. That gives you a more volumetric probe of the atmospheric disturbance over wider field of view. And for each guide star, you can have a camera to characterize its wavefront. And you can also use multiple deformable mirrors. And one, for example, here is conjugated to the ground layer. Another one, DM2, is conjugated to high altitude, say at 11 kilometer. And that is what the TMT's multi-conjugated AO instrument looks like. This system is in-kind contribution from Canada, and it's all designed out. This structure with a person standing there is about 8 meters on each side. The AO corrected light can be sent to 3 ports, the top, side, and bottom. At the bottom, you see a science instrument iris attached to it. To generate the laser guide star, you need a facility. It's called Laser Guide Star Facility, and this is a responsibility of China. And we are the U.S. project office is actually working with them very closely and essentially taking over the work to keep making progress. You can see below the primary mirror, there's a set of lasers, and the lights are guided through the beam transfer optics through the side structure all the way to the top end behind the secondary mirror. And this is just a clear way to look at this, up to 9 lasers and through the beam transfer optics to the top end. And the top end structure is shown on the left. You manipulate the lasers and project it through the laser launch telescope to the asteroids that you desire. And this is a fairly complex system. And in the project office in US, we contribute to the Canadian multi-conjugate AO system many key components for this instrument. One is for each laser guide star, we need a very high-speed camera. And a few years ago, we were developing custom-made CCD chips to be able to read this fast and efficiently. And eventually, the industry technology caught on and caught us up, and now we have available these Sony CMOS-based cameras made by multiple vendors. And these cameras meet our requirements. So instead of developing these custom-made chips, and we are using commercial now, and it really helps us improve our risk posture and cost as well, and eventually maintenance. On the right, it shows we have in this multi-conjugate AO system, we have 2 deformable mirrors, and I cannot show better pictures than this, but the bottom is a prototype this company called Silas built for us. And it passed the test and meet most of the requirements. And so now the company is under contract to produce 2 of these. One is a deformable mirror, has over 3,100 actuators and 5 millimeter apart. And so this is, the oversize is about 30 centimeter across, and it has to operate at minus 30 degrees C. Another one conjugated 11 kilometers, and it's 4,500 plus actuators, and it's also 5 millimeter apart. So that size is closer to 40 centimeters. And so both are in final production in Europe. Now look at the first light science instrument. The AO light is fed into these IRIS instrument, infrared imaging spectrograph. And this one has a take advantage of full diffraction limited capability. The imager has a 34 arcsecond field of view. At the center, there is an integral field unit, and it has two types of lenses, a fixed lenslet pickoff and a deployed slicer pickoff. And with this, you have down to as low as 4 milliarcseconds per spectral, and fully taking advantage of the diffraction-limited capability. So this next slide shows how the IFU works. And with lenslet, you have an array of small mirrors. And for each lenslet, the light is fed into a spectrograph. So you have many of these spectrums, position-based spectrums. And this gives you a spectrum with space information, and it's a lot of data involved. For mirror slideshow, you lose some of these spatial information, but it gives you more sensitivity. So the next AO-fed diffraction-limited instrument is called MODIS, and this is recently selected to enhance our capability to exoplanet research. Because this is single fiber-fed, very small field of view for arcsecond, and study single object, you have a very small, instrument size is very small. And it gives you, it uses a shell based spectrograph and spread lights in two directions. And it gives you very high spectral resolution, well over 100,000, and precision radial velocity down to 10 to 30 centimeter level per second. Again, this is good for exoplanet research. The first light, the only seeing limited instrument, is wide field optical spectrograph. In comparison, this is a much bigger instrument, and the lower bottom, left bottom here, it shows a 2 meter scale, so large optics. And this instrument has been recently updated to a modern design. And one key feature here is that since you have two cameras, one for blue end of the spectrum, one for red end, the two cameras now rotate on horizontal planes. And so this makes it gravity invariant and gives you capability to do spectrum on up to 60 objects over a wide field of view of 25 arc-minute square, with a medium resolution, spectral resolution. This instrument is also very sensitive to interest in UV photons down to 310 nanometer. Our current design for telescope assumes a Gemini-based coating, and that has a cutoff of 340 nanometer. And recently, our group has been working with a vendor in Europe, leveraging their industrial strengths and working with multiple observatories. And they produce a set of coupons, and we test it out, and it actually does give you a cutoff at 310 nanometer. It's very promising. Of course, we need to go through durability test to make sure that it is practical on the telescope. And if this works out, a lot of the observatories will benefit. So finally, this is a very large, very complex project. A lot of international partners are involved with different degrees of maturity and capability, and proceeding at different pace. So system engineering tools are very powerful and very important for us. And this, I just list some of these. We emphasize design requirements, well-documented design descriptions, interface definitions, a verification process at different stages of assembly. And all these designs, wherever possible, are supported by a lot of analysis, modeling. Some of you have seen here, simulation, prototyping, and testbed. And large, complex structures, all of these are done. And we also keep track of performance budget, engineering resource budget, reliability budget, maintenance budget. We also do failure mode analysis, hazard analysis, and risk management is a current event. And we always identify risk and find ways to mitigate them. So in summary, TMT design is mature, is well designed and analyzed. It promises to bring new discoveries and change the landscape of astronomy for the next at least 50 years from the northern hemisphere. And so distant shores are waiting for us. So with that, I will stop the presentation and take questions.
Well, thank you for a very thorough overview of this astonishingly large and complex project that promises to bring new vistas to us once it sees first light and those instruments get turned on. So we have a Q&A session now. Carl Merrill, a molecular biologist, has a question. Carl, could you go ahead and ask your question?
Yes, this looks like a magnificent telescope that you're building, but I know that during the initial construction and throughout it, there was a lot of social and political problems. And so the question is, have they been totally resolved, or is there still a lingering problem with that? So that's one question I had. And the other one is, could you contrast and compare what this telescope will do versus what the Webb telescope can do that's being launched right now?
I will answer briefly the first question. No, we still have the challenges. We are having a much better understanding. I'm based in Hilo. And so I will just say that because Larry reminded me, this is a science talk. We can, Carl, if you know how to reach me. If you want to talk about this more, we can talk offline. But in terms of comparison to Webb telescope is a space telescope, its wavelength is infrared. It goes to 28 microns wavelength. It's in this wavelength, you are very sensitive to thermal emission. So these telescopes do not operate very well on Earth, and so you have to go into space. And that's what they are specialized in. We are more of a optical near IR telescope. We can do thermal IR, but the capability would be not as good as Webb because of the atmosphere.
Thank you.
So I have a question from Dave Rabinowitz. Dave, could you unmute your mic? Oh, I'm supposed to ask this question. Does the altitude of the guide star have to be modified based on atmospheric conditions? And if so, how rapidly?
The guide star is 90 kilometers, and it's not a point. It's not a thin point. It's actually a little column. And so you have to take that into account in your AO system. And for this near IR regime that we do, AO does work. And frequency, the bandwidth is close to 1,000. And we run it at, and in that CMOS cameras, we run it, I believe, 600 hertz.
Could you comment a little bit on if you can't site this in Mauna Kea, if you've done all these engineering studies, how much does they have to be modified if you have to put it somewhere else? Or is it fairly land independent?
Yeah, thank you. That's a good question. We want to be in Northern Hemisphere. And if we have an alternative site, that's La Palma in Canary Island. And there's not a whole lot of change we have to do. The key driving factor here is a seismic environment, and La Palma ORM is much more benign in terms of seismic. So it's actually more of a simplification. Of course, in the science instrument, because that site is lower and there's more atmosphere above you, you have to optimize slightly differently on things like atmospheric disturbance. So it's some modification, but there's no major wholesale change.
Interesting. Now, does the atmospheric disturbance has a profile as you go from the telescope up into the atmosphere? Is a lot of it in the vicinity of the housing?
Yeah, there's a lot of the ground layer, but it goes all the way up to 11 kilometers.
Does it get worse if you're in the Canaries versus Mauna Kea? substantially worse?
Not substantially worse. My understanding is that there's more air in because of lower mountain, that's for sure. But the air in La Palma is also very smooth, very steady, and it's good for AO correction. But because there are a lot of more airs above you, there's more water vapor to absorb infrared light. So the performance you lose is more in the infrared, mid-infrared range. And that is somewhat important because the exoplanet field really cares about that. And that's a explosive field for new science there.
So how do you get all of these different parts together and get them up the mountain, whether it's in the Canaries or in Hawaii? And how many people will be working on constructing this thing at one time?
That's a good question. I think we designed it such that there's no single piece that's large enough. You cannot ship it up. And in fact, when we first considered alternative site in La Palma, our engineers went up there and check out the road and turns to make sure that our largest piece can go through it. And in one case, we may have to, redesign a single large piece into two smaller ones. And I don't know the final result on that, but that's how much details we care about. And so right now we're not at the full production rate, and we have I would estimate more than 100 people around the world working on it. But eventually that number will grow by probably a factor 2 or 3. And when you count all the vendors and partners and all this, yeah.
I
you cannot
just
rush
wondered
it.
how many people will be on the mountain at one time when they're building.
That I do not have a number, but it's not many. And it's we really try to minimize this, do as much work and sea level as much possible, and try to minimize impact on the mountain. I do not have a number, but we try to minimize that.
By the way, Olivier and Jim Fanson are both on the Zoom call. I wonder if either one of them has something they want to say or have a question. Hello? I sort of caught them by surprise here.
Yeah, well, I think just looking at our profile, the workforce profile, we'll be talking about dozens of people up there at maximum.
So we have a question from Ellis Trancho.
Yeah.
Can they unmute their mic? And
I work for Fengchuan. I was trying to say that the number of people that will be working at the observatories between 20 to 40 people at one time.
okay.
Thank you, Hellis. Hellis, our lead system engineer.
Hi. Thank you for joining in. So it's pretty high up there. I wonder if they require oxygen supplementation or they're all acclimated.
It depends. I've been up there a few times, and there are people who go all day without oxygen, and I go up there, I need oxygen all the time. So it depends. And it also depends on what type of work you do. And if you really need the highest concentration, I think having oxygen will certainly help.
Olivier.
Yeah, thank you. I had a question. It's the project development is spans multiple years. How do you decide when new technologies, you mentioned the CMOS camera, come online? How difficult is it to design, to redesign things and go back and improve, and what's the decision process for that?
Yes, that's a great question, Olivia. We look at this case by case. Some cases are really easy. Laser. We were doing custom design lasers, development laser in China, and when the laser from Germany becomes available, it's an easy call to replace it. And in this case, the cameras. We did a few months of pretty thorough treat study and look at if we were to change it, what else needs to change, and you look at anything that could be impacted, and come back with all factors on the table, and you make a judgment. In this case, the benefit way outweigh the the impact. And so that's how we do.
Yeah, I have a question from Carrie Liss. Trying to find it because not. Neil from Columbia asks, can we please see the atmospheric thermal housing video game? And can you elaborate on how it works? Well, I think that's a good question. And I also was going to ask whether there are any active heating or cooling elements, or it's all based on those.
Yeah, let me find it. It's a lot of slides here. Okay, I got it. So there is no active heating or cooling in this image. I mean, they are passive heatings from elements in part of the telescope. So we have high power components in the telescope. We use coolants, or we use CO2-based refrigerant to take the heat out, so they do not dissipate the heat into the air. We have a budget for heat generation allowed for each major component. And that's how we control the heat dissipated into the air.
Jim Fanson says he can't unmute his microphone, but he wonders how the TMT plans to deal with the issue of satellite constellations that are being built and sent up to low Earth orbit, most noticeably those of SpaceX. I added the part about SpaceX.
Yeah, this is clearly a growing concern, not just SpaceX, and there's a competition seems going on around the world to launch more of these satellites. So we're watching it closely, and the little bit of benefit we have is our instruments, our telescope, are relatively small field of view, and we monitor them and we can avoid it actively. And the chance, because the field of view is small, that getting to our field of view is quite small. I think wide field instruments would have a more of an issue, like the Rubin Observatory and others. So we have done a study on this, and so far, with the number of satellites we know, it's not a major concern.
We have a question from Carrie Lease, the non-traditional TMT dome structure. It improves the dome laminar airflow, but doesn't restrict the ability to observe from 3-hour angle to minus 3-hour angle to plus 3-hour angle, and 10 degrees azimuth up to 90 degrees azimuth. That's a question, which I didn't read very well.
I'm not sure I understand the full question, but I would just say we have 3 moving parts. The azimuth.
Wait. Carrie, can you unmute your mic?
I did. Can you hear me?
Oh, sorry.
Yes.
Sorry.
So wonderful talk. I'm a longtime observer at the IRTF. I also use Keck. The question mainly is that when one looks at the telescopes on top of Mauna Kea, there's never one standard construction for the dome, right? Everybody's got the different way of looking. Subaru went to optimize the airflow. Keck's more traditional. The IRTF is a very traditional dome shutter, 360 rotation mount. You clearly don't have the same design that the EELT is going for. And so I was wondering whether you've got this better laminar flow structure. You're making sure that the vorticity, and you've got a wonderful air quality inside your dome. But it looks like you are paying the price that you can't just simply go from 0 to 90 degrees overhead, and you can't just rotate the dome and see everything you want at a given time of the night. It looks like you're a little restricted, or is that not true?
I think we showed the one simulation. There are a lot of these different elevation angles, and our design limits us to from 1 degree to 65 degree zenith angle. So we have look at these at various angles.
Okay. The other question I have is, when I apply for time, am I going to your telescope is set up for totally remote? Am I going to go to Waimea like I do for Keck and then observe from the ground level, and there'll be a TO up at the telescope, or will I actually be at the telescope?
I think we're all moving in the direction of what sometimes they call it pajama observation.
Yep.
You can do it at home. Yes.
Kitchen table observation. Yep.
Yeah, I think the pandemic is certainly helping that direction. Yeah, we're all moving in that direction. I'm sure 10 years from now, that'll be more so.
Will you then have this? I use 2 different telescopes. Keck actually has dedicated remote observer sites, The IRTF actually has just an application called VNC, and I literally observe the IRTF, well, last month from my kitchen table. So which would you be using or implementing, do you think?
I want to say this, but I think I'm going to defer this question to Christoph, who is our observations chief and observatory scientist. He can give you a much better answer than I can. Christoph Dumas.
Oh,
Okay, can you hear me now? Hello?
Yes,
Yeah, we can hear you.
Okay,
Yeah.
yeah, well, I just found out the unmute button. Okay, so I was very lucky. Yeah, so hi, everybody. So in terms of observing, I mean, can you, because I was trying to look for the unmute button, I just want to make sure I'm going to answer the question properly. So what was your question exactly about, like the observing modes? That what was it was about?
no, my question was, can I observe from my home or from my own institution,
Okay.
my office, or
Yeah.
do I have to go to a dedicated TMT remote observer site, which is the KEC model? The
Okay.
first is the IRTF model.
Yeah, currently our baseline is to offer the same services that you are used to get from CAC. Okay, that means going to a dedicated place where you can actually connect and observe, remotely from that place. But we are still quite a few years away, okay, from the start of operation, and this might evolve into something more like Fengchuan mentioned, okay, that you could actually observe from your kitchen table. So the only difference between the two is just developing the software so people actually can do this from home, and making sure that you get the right, sort of performances on, to connect to the observatory. But in any case, the amount of information, the amount of control you will have as an observer, remote observer, will be limited. Okay, so you will not be able to control the telescope. Okay, what you will be able to do is to select the next set of observations, look at the quality of the images you have obtained, communicate with the observer at the observatory, and provide feedback and comments. Okay, but you will not be able to control the instrument or the telescope.
So the observations will be queue scheduled. They won't be like the IRTF where I'm actually literally interacting with a TO in near real time and moving the telescope.
We are going to offer that, okay, as well, okay, because that eavesdropping, that means you will be able to connect in real time and be able to communicate with the observer, even if you're not doing the observations yourself.
Great, thank you.
You're welcome.
Great.
Could you say a few words about the data production that this telescope is going to be pouring out, and how you get it down the mountain? And when somebody's observing remotely, what are they actually looking at? Because they're probably not looking at that huge amount of data that's coming out of the telescope.
Again, Christoph is the expert on this.
For those of
Yeah,
us who aren't observers.
Yeah, hi, okay, hi again. So basically what's going to happen is, as soon as you observe at the telescope, whether you observe, in any mode, eavesdropping, service mode, or visitor mode, all the data are going to be copied to two archive machines, one residing at the telescope itself, another one will be available to all users around the world. And people in real time will be able to download the data, assess the quality, play with them, reduce them, and optimize the strategy. This is also true for the calibration files. Okay, it's very important to get the right calibration in order to process your data. And the calibrations we are going to be obtained a few hours after the science observations. First, you need to understand what kind of science configuration you have been using during the night. And the morning after, we are going to calibrate the data for these specific configurations. And all data are going to be made available immediately to the users. The data are going to be processed as well for all the observing modes automatically. And all these reduced data are going to be made available to the user through the archive. So that's the work. I would say that is the data flow, okay, from that we are looking at.
I was kind of curious about, how much data is coming out of there, like from a night's observing, and how much storage do you need, and what kind of processing power do you need to do the sort of processing you just mentioned?
Yeah, that's a very good question. Let me look at just in order to be able to answer exactly the amount of data we're looking at.
I mean, our data, we have IFUs that generate a lot of data, but it's not the same compared to actually some of these small survey telescopes or large field of view survey telescopes. They generate a much bigger.
Yeah, that's what I was wondering about.
Yeah.
Like,
So I don't think we
the
are.
Rubin telescope is going to.
Yeah, Rubin Observatory, or even Pan-STARRS, and seeing small telescope, but very wide field of view and short exposure.
Yeah, that's a very good point. Okay, we are more like traditional. Okay, so we do have some modes. Okay, like the adaptive optics modes, where some users will be interested to have a very high definition in terms of data and time resolved data, but most of the time this is very classical observing. So I found the information. I just wanted to make sure that I was going to give you with the right number. So we are looking about on a yearly basis. Okay, we're looking about 100 terabyte per year. Okay, which is totally manageable. Okay, with, even with today's technology.
Yeah, it's very manageable. Our next speaker does molecular modeling, and she's talking about petabyte and exabyte scale computing for looking at whole viruses and how they bind to cells and enter. Doing molecular modeling on that. It's gigantic.
So to complement my colleagues, with all the instruments working and everything, calibrations and everything, the maximum rate that we can do is 1.7 terabyte per year. That's the maximum, but that means everything, the full set, everything, all modes, everything.
That's a respectable amount of data. So we have a question that from Jorge Aponte, who I think is in Colombia. And he wants to know, a question that often comes up is, in essence, why not spend the same money and put a telescope in space? I think I know the answer to that question, but.
Well, I would say before this job on TMT 6 years ago, I spent 20 years at NASA JPL on space missions. And I think my friend here, colleague here, Jim Fanson, is expert in this as well. So the challenges are very different. If you put a telescope in space, you have to worry a lot of things about how to survive launch. And when you go up there, there's no service. So if something goes wrong, you cannot afford that. So there's a lot of safety, maintenance related issues. And so in the end, you end up spending a lot more money in those factors. So the capability of building large telescopes in space is very difficult. You have to fit into the fairing, survive it, and unfold it, and everything has to work right the first time. So there's a different set of challenges.
It's a kind of an interesting proposition to put Hubble up. One space shuttle launch is between $1 billion and $2 billion at the time. And I think TMT here is costing under $1 billion. And Webb has turned out to be a $10 billion proposition. And so the cost differential for the scale of telescope is pretty high.
It's that, and also the upgradability and maintainability, and be able to take on some risks that because you can fix it. That gives you a lot more options.
I think as the commercialization of space moves apace, so the equation may shift a bit.
Yes.
I mean, certainly the cost of launch has come way down, and the near-term prospect for assembly in space and easier access may indicate another look at that proposition.
Yes.
So we have a question from our friend down in Australia, who is also in the field, Frank Robert. You can turn on your mic, Frank, and ask your question.
Thanks very much. Just a fabulous talk, by the way, very rich. We really appreciate it. And I was asking about the digital. You had quite a few graphics that appear to be generated by digital twin methodologies, that simulation of the airflow in the telescope, the stressing in the telescope, the light paths through it, and so forth. So I was just, my question was whether this is a concurrent design approach where the modules of the digital twin interact with each other in real time, the way you do for a spacecraft, or whether you can leave them as separate modules and just model each one by itself.
I would say we do both, and we certainly model each one by itself, and in some cases we do models connected all together.
Thank you.
And there are, for examples, for seismic analysis, and if you have a well characterized attachment, you can do analysis by itself, given the interface requirements, what the seismic environment you will see at that point. But for large complex structures, well integrated, you want to do couple load analysis, you put them all together.
Wow, so you have to compensate for the seismic load. Sorry, Larry, I'm adding.
No, go ahead.
Need to add a question. You have to compensate for seismic activity at the telescope?
Yes, we do a seismic isolation. Isolation is different from what you heard on GMT, but we use dampers at the bottom of the pintle bearing. We have a set of 4, and each one has parallel dampers.
Wow, thank you.
Thank you.
Do all the partners have the same access to the digital twin?
I wouldn't say that, because we have industrial partners involved, and so there are intellectual property involved. In some cases, it's you can share it freely. In some cases, you have to honor and respect the IP.
Sure. But in general, is the Canadian group working on what they're working on able to see how it's going to fit into the general scheme by plugging into the same software and data set?
We make sure if you need that, you'll find a way to get it.
Okay.
But it's not something that it's just there, anybody can get it, no.
Got it. So I think we'll close with a question from Carrie Liss again. Carrie?
Actually, two, if I can sneak one in.
Sure, go right ahead.
The first question is relatively straightforward. You mentioned your data is going to be stored into an archive as it's taken. Will that archive be available publicly after a proprietary period, say 18 months, like the Keck Observant, the KOA archive, which has been quite fruitful for researchers extracting data? I think there are more papers now written off the KOA than there are from the straight observation.
I would say that we do not have definitive answers. Yes, in general, you have preparatory period, and 6 months, 12 months or longer. But because we are in the process of engaging the US EELT community and then NSF Optical IR Lab, and they have federal guidelines. And so this conversation is just beginning, and the answer is not going to be limited to a private observatory, and it will have a federal component as well. But yes, in general, we want to give the PIs, if you will, some period of time for a proprietary period, but eventually data will be made public.
Absolutely, that sounds great. And I just want to make a comment, if I may, is being familiar, I was on the Keck Oversight Committee for many years, and being familiar with how Keck has had to deal and take care of the issues with their 36 deformable mirrors and the cracking and the actuators. I just want to say I'm absolutely impressed with the fact that you're going to be dealing with an order of magnitude more mirrors and babying them, taking care of them. Are you going to do that in-house like Keck does, or are you going to actually send out, if there's actual detailed work that needs to be done on the actuators, are you going to do that industrially? Do you have any idea of that?
Yeah, the actuators, these are designed in-house, if you will, but fabricated in industry. And some of them are actually fabricated in India as we speak.
I see. But are you looking, there might be issues with them in the long term, 10, 20 years down the road, like Keck has found? Or do you think that you're going to use all the lessons learned from Keck and the bonding pattern, you're going to improve on that, so you won't have problems? Oh
yes, the bonding pattern specifically, we have very close relationship with Keck in many fronts. And in that specific case, our engineers, Eric Hansen here on the call, have been there and talked to them multiple times. And we are taking all the lessons learned, and we are, in some cases, modifying our design installation, how to do the bonding. And we do a lot of testing just to make sure we don't repeat the same issue.
So translation, Larry, maybe this is well known. I don't think it is. Keck has been a fantastic observatory. The actuators work very well in 36 mirrors, but over the course of decades, they found the way that they glued the actuator, think of them as little pistons in the back of the mirrors, what led to cracking of many of the mirror segments and issues and deforming of the optical quality. So they've learned there are better ways to actually mate the actuator to the mirror back. And
yes.
When you say the way they glued it, is that because there's different thermal coefficients of thermal expansion, or the glue aged differently, or there was a chemical reaction? I mean, what was it about the glue that caused the mirrors to crack?
Yeah, I think in this case, I'll just answer very simply. And if that's not enough, I think I invite Eric Hansen to answer this. And you have to really control the amount of glue that goes into there. Eric, do you want to add to that?
No, that's absolutely correct. It's a combination of the stress that the different thermal expansion components, as you mentioned, the glue being one of them, put on the glass, and the sensitivity of the glass to fracture. And over time, that was an issue with Keck. We've certainly taken the lessons learned, done significant analysis that was not done to avoid that, as well as considerable accelerated aging tests to make sure that we don't have a similar problem.
Very good.
Thank you, Kerry.
You're welcome. Best of luck to you. I can't wait to see your telescope up and running.
Thank you. Thank you.
I think we all would second that. Amen. So thank you so much for giving this talk. Spending your time with PSW. It was a great lecture. And I'm really glad that you came and spoke.
Thank you, Larry.
We regret that we can't have you here in person, but you have a rain check to join PSW anytime you're here in the future.
You bet.
That includes the pre-lecture reception and dinner. And I'm going to extend that invitation to your colleagues who are kind enough to join in.
Yeah.
And so if they happen to be in DC, please feel free to get in touch with me once this plague is gone and we can get together in person and enjoy it.
Yeah, you can count on me. Thank you, Larry.
The fall lecture series has been posted to the PSW website. The 2,448th meeting will be on Friday, November 5th. The speaker will be Ronnie Amaro. Rami holds the endowed professorship in the Department of Chemistry and Biochemistry at the University of California, San Diego. And she will be speaking on virus dynamics, including how SARS-CoV-2 binds and enters cells. The 2,449th meeting will be on Friday, November 19th. The speaker will be Robert Beyer, Keenan Professor of Applied Physics and Photon Science at Stanford University. He'll be speaking on a very interesting topic, laser-driven particle accelerators on a chip, much, much smaller than the LHC. The fourth 2,450th meeting will be on Friday, December 3rd. The meeting will coincide with PSO's DuPont Summit, to which all PSW members are invited gratis. The speaker will be Francisco Cordova, director of the Arecibo Observatory, and he will be speaking about the observatory's history and its prospects for the future. The 2,451st meeting, closing the fall lecture series, will be on Friday, December 17th. The speaker will be Sean Andrews, astrophysicist at the Harvard Smithsonian Center for Astrophysics. He will be speaking on the current understandings of how planets are formed, both in our solar system and around other stars. Please join us for these meetings. And before we go, let's not forget to thank tonight's crew for producing tonight's event. James, Robin, and Ann, thank you so much for your hard work on this evening's presentation. And with that, I will join the meeting I wish everyone a good morning, afternoon, evening, and night, wherever you happen to be. And until next time, the 2447th meeting of the Society is adjourned.